presenting will spark some good questions. So, this slide here presents on one scale gross domestic product, on the other scale roughly time broken out by what I would call the 4 industrial revolutions. Something that's very important here is a lot of the advances that have allowed this significant increase in GDP were technology driven. And so on this scale, we have a number of milestones, but what's special about those milestones is that those were led by RPI faculty or RPI alum. So down at the low end, just after the founding of RPI in 1824, you see construction of the Brooklyn Bridge, and the chief engineer was Washington Roebling, class of 57, civil engineering. Then we go up a little bit further, the lunar landing, 1969. And down below we have George Low, who an argument can be made, single-handedly saved the Apollo program after the disaster of the fire on Apollo 1. And then he became effectively the father of Skylab, the Soyuz missions, and the space shuttle. Then we've got Ted Hoff, one of the inventors of the microprocessor, which is now ubiquitous. Where would we be without microprocessors nowadays? We would certainly be without our smartphones. Steve Sasson, class of 72 and 73, the developer of the first digital camera. Yes, that is the first digital camera. Aren't you glad you're not carrying that around in your pocket? And then Curtis Preem, graphics processing, one of the co-founders of NVIDIA. Who's ever heard of them? Okay, so again, very, very significant. There are others, but one that I'll finish off with is Reed Weissman, Commander Weissman. I remember Reed as a student. Before he was picked to be the commander of the Artemis II mission, he was the chief astronaut for NASA. Okay? Unfortunately, being the chief astronaut, he was the one that was assigning different astronauts to the mission, so he couldn't assign himself to Artemis. He missed flight time, he stepped down from the position, and he was tapped to become the commander for Artemis II. He was a really great guy. And hopefully somewhere out in the future I can put up a picture of you. So, there are a number of challenges out there that face the world. The National Academy of Engineering identified 14 grand challenges that must be dealt with by this generation. I've chosen to list just 4 of these because these line very directly with the 4 principal thrusts that RPI is pursuing. We have energy and sustainability, human health, climate change, and security, whether that's cyber, physical, or biological. The thing that's important is, as significant as these are, and as important as these are, is having enough engineers and scientists to deal with them. Those numbers. Last year, there was approximately 2,167,000 Bachelor's of Science graduate degrees were given. Of those, fewer than 6% went to engineers. So we desperately need more engineers and scientists. You know, we need you. Fortunately, engineers get paid very, very well. So these are some of the averages from last year. There's quite a spread between the high and the low, but these were running averages. These averages tend to run about 10,000 or so higher than the national average for the same discipline. So our graduates do considerably better than the average in the same discipline. Yes, it's nice to get paid, but it also helps if you love what you do. But the nice thing about being an engineer is there certainly can be a mercenary side to it because we get paid very, very, very well. Another thing that's important, and it's understood that RPI isn't necessarily a cheap place to go to, but historically and currently we are considered one of the top institutes in the country for return on investment. That if you go out there and you do a search on return on investment, of course there are different organizations that have slightly different metrics, but you'll see that RPI is generally way up towards the top. Because many companies love RPI engineers. So these are examples of all of our accredited engineering programs, or all of our engineering programs. Many of these programs are ones that you would expect, you've heard of, you're aware of: civil engineering, electrical engineering, mechanical engineering. But very likely some of these disciplines are things that you've never heard of or not familiar with. Material science engineering, what is that? Industrial and management engineering, what is that? Environmental engineering, what is that? Biological and chemical engineering. Okay, so the fact that you haven't heard of these or unaware of these shouldn't make you uncomfortable. We understand that, and so our programs are very much set up so during the first year, year and a half, you can explore, learn about the different engineering disciplines, discover your passion, and then move into that field. Our programs are all set up so it's exceedingly easy to move from discipline to discipline to discipline. Arguably too easily, because there's nothing to prevent you from 2 weeks before graduation deciding that you want to change your major. I'm not sure I would recommend it, but you can do it. You just come into my office, talk to my administrative associate, and it's done. Our goal at RPI is that every engineering student graduate in the major of their choice. Now, we will see in a minute when I put some numbers up that there is a downside to that, and that is that some majors end up having a lot more people in them than maybe the faculty can easily accommodate, because those numbers have grown very, very quickly. The point is, our programs are very comprehensive, they're very flexible, they're very diverse, and it's very easy to move from one to the other if you wish. So here are enrollment numbers for the entering class that started this year. These were the official numbers maybe a week to 10 days ago. So you look up there, the total as of a week or 10 days ago was 1,549 for the Institute. 919 are engineers. So the other schools may hate this, but it's pretty clear we are first and foremost an engineering school. And we always have been. That's why we're the engineers. And so this is the breakdown. Within engineering, this is what the numbers were for the entering class. And so you look up there, again, there's a lot of majors that you would recommend or recognize, others that you might not. For instance, let's drop down and let's talk about materials. Only 14 people declared material science engineering when they applied. Now that doesn't mean that material science engineering isn't as valid or as important as all the rest. In fact, an argument can be made that's even more important, because many of the advances that are being made in all the other engineering disciplines is only possible because of advances made in materials engineering that allows the electrical engineers, the mechanical engineers, the biomedical engineers, the civil engineers to push the frontier forward. Same thing, another one up there. Industrial and management engineering, only 10 people. It's not because it isn't important, it's probably because they weren't aware, or you were not aware, that there's something out there called industrial and management engineering, or your high school counselor is unaware of it. They're critically important in making sure that large, complex problems can be dealt with multidisciplinary teams, and that everything comes together in an organized manner. Incredibly important discipline. But again, a lot of disciplines. We've got 12 of them up there accredited in PDI. It can be a little bit intimidating. So again, our goal is that you come in, you spend your first year and a half figuring out what your passion is, and then you move into the passion. One number I would like to key in on is that undecided engineers, 80, down at the bottom. It seems that for whatever reason, the group that came into RPI this year largely knew what they wanted to do. Historically, that number at the bottom has been as large as 20% of the applicants. 20%. More importantly, if you look at the number of students that came in as undecided or changed their major during their first year, they thought they wanted to be engineer X and decided to change to engineering Y, the number would jump to over 40%. So not a majority, but a super minority. And again, this is not a problem because we are set up for this. We understand that a lot of engineers, many engineers come in and they think they know what they want to do, and it isn't until they get into their first year or even the first half of their second year, they say, no, I really think I'd be happier over here. So, how things appear. Unfortunately, if you go out and look at web pages or talk to engineers, particularly engineers that were educated 20 or more years ago, you might get the idea that this is how things are in engineering. Civil engineers are over here, electrical's over there, nuclears are way over there because they're radioactive, and chemical engineers, they're over there too. And they don't communicate. This couldn't be further from the truth. This depiction is largely historical and to some degree imposed by ABET, which is the accreditation agency. When you drill down and you start looking at real, complex engineering problems, this couldn't be further from the truth. There are very few significant engineering problems which are monolithic in a single discipline. Generally, you need multiple engineers from multiple disciplines and scientists and business types all working together because the problem is bigger than any one person and any one discipline. You will find that here at RPI, particularly if you do undergraduate research. We have a very, very vast undergraduate research program. We highly recommend it. And you will discover if you do get involved with undergraduate research, or even if you don't, I would say if you come to RPI, raise your hand. Let's say you're taking a civil engineering course. Raise your hand. Pardon me, professor, can you give me an example of where this technique that you're teaching us is applicable outside of civil engineering? And you will be surprised. They'll answer for you that fast. Why? Because most of us are doing research. We're a Research One institution. And that most of the interesting jobs lie on the boundaries between disciplines. If I could use myself as an example, I am an aerospace engineer. I came here from the aerospace industry. There was about a decade there where most of my funding wasn't coming from aerospace, it was actually coming from the medical profession, and I was building very large, very complex molecular dynamic models. And I was modeling enzymes, RNAs, DNAs, proteins, viruses, and that. Why? Because methods I had developed for my PhD more than 40 years ago and have been applying to spacecraft and rockets also lend themselves well to modeling very large, complex molecules. Okay? This is not the exception. This is the rule. So if you were to come to RPI and you start talking to the faculty, you discover, yeah, you've got different departments, maybe in different buildings, but they're all highly connected. That there's tunnels, roads, bridges, internet cables, all connecting them, and we all work together. Case in point, again, I came from the defense sector. You come here, you'll learn very early that most engineering problems have a design component. Something failed, we need to make it better, or something doesn't work as well as it should, we need to make it better. So design is always in the background. I guarantee that if you go to most institutions, you'll have a mechanical engineering design course. And everybody on the team is going to be mechanical. You're going to have a civil engineering design course. Everybody on the team is a civil. You're going to have an electrical engineering course. Every member on the team is an electrical. I guarantee it because I'm a team chair for ABET, the accreditation agency. Every year I lead teams to evaluate other schools, and they do this. Okay? Not at RPI. At RPI, because multidisciplinary design is so important, at the sophomore level, you'll be taking your first team-level design course. And if you're a mechanical engineer, you're going to be put on a team with 3 other people, and I guarantee you'll be the only mechanical engineer on the team. You may have a civil, you may have a biomed, you may have a materials, you may have an industrial, you may have whatever, but it's not going to be another mechanical. The teams are always going to be assembled to be truly multidisciplinary, and you've got to work together on a relatively simple design problem, but you get to choose it within your zone. Similarly, you get to the graduate level. I teach spacecraft design. On my team, yes, the application is spacecraft because it has to be, because we have an accredited aerospace, or if we're to build an accredited aerospace program. But given the nature of the subsystems, I have mechanicals, I've got electricals, I've got computer and systems engineers that are working on our spacecraft. And indeed, a little bit of a plug, I'm co-teaching the course this term with Rick Mastracchio. Does anybody know what Rick Mastracchio is? It's okay, he is one of our astronauts, graduates from RPI. He's now retired, he's a VP with Northrop Grumman, and he and I are co-teaching this course together. So if we look at this, here's an example of an aircraft, a complex system. You've got an aerospace engineer that sort of needs to be involved because they know how everything goes together. But then you also have electrical and computer and systems engineering because avionics is so incredibly important to modern aircraft and modern spacecraft. You've got material science because we're truly pushing the edge in material science, again with aircraft and spacecraft. Civil engineering, oh my God, when was the last time you saw a building fly? Hopefully not recently. I used to work at a facility in Redondo Beach called Space Park. You can sort of guess what we worked on. We actually had more civil engineers on site than we had aerospace engineers. Why? Because the base-shaped problem that you see for a large rocket launch is very similar to the base-shaped problem for an earthquake shaking a high-rise building. So we were piloting civil engineers from the earthquake sector right, left, and center because we needed them for our systems. And so we had a load of civil engineers, and they did an outstanding job modeling large rockets and some aircraft. Of course, mechanical engineers, we had more mechanical engineers than anything else because as soon as you drop down to the subsystem level, that's dominated by mechanical engineers and electrical engineers. If you're dealing with a manned system, you have to have biomedical engineers involved because space is a pretty nasty place. You really need to work to keep people alive and healthy in space. And then, there's industrial and management engineering. Helping us all work together. This is how you are going to experience design at RPI. Design is not a single discipline, it is multiple disciplines, even multiple schools working together. Okay, so these are the types of things, at least in my humble opinion, you need if you're going to be a successful and happy engineer. Satisfaction solving challenging problems, because that's what you get paid to do. You're solving other people's problems. You need to be creative. Why? Because the easy solutions were already solved. You have to like working with people in teams, because again, all the problems are going to be bigger than any one person, and they're going to be multidisciplinary teams. You need to be adaptable. You get into things change, you discover things aren't going to work. You need to be a critical thinker. That if you've been working on a design and the design tells you, the analysis tells you this design really isn't going to do it, you have to be able to acknowledge that and change direction. You have to be able to think abstractly. How do I get there from here? In fact, this is another one of those things that I think is very special about an RPI engineer. We produce what I call T-shaped engineers. What is the T? The stem of the T. You find your passion and you become deep in the knowledge and the skills associated with that discipline. What is the broad part of the T? Well, you recognize how you can affect all these other disciplines. You may not be able to solve the problem directly, but you can see the connection and you realize that if I choose the right people, we can get there from here. So again, this is very much our focus. Oh yeah, and of course, you need to be mathematically inclined because math is the language and physics is the rule book. And so if you're doing modern physics-based engineering, you know, physics is not very far below the surface. And math is the language that you use. All right, so here's a question for you. How many of you think you want to be an engineer because you hate to write? Okay, you're better people than me. I sure hate to write. Unfortunately, you got to be able to communicate. Written form and verbal form and graphical form. I like to say that all engineers are mad, M-A-D-D. And what I mean by that is we model, we do analysis, we design, and we document. And you only get paid for the last D. As someone who came from industry, those other three don't exist until you've got it down on paper or on the computer in a form where another engineer or scientist can replicate what you've done. Anything short of that is short of the industrial standard. So when you get into industry, you are going to discover that you are going to be writing often. It's going to be a different type of writing. It's going to be memos and reports, but you will be writing often. You will be communicating often. Verbally, in graphical form, making presentations, and in report form. Okay, so the hard skills, things you might expect. Math and science, discipline knowledge, advanced tools, coding, modeling, etc. Another thing that we do very well here is we emphasize the soft skills. Leadership, communication, working with teams, taking responsibility, professional ethics. These are a huge part of all of our engineering courses, particularly our design courses. And indeed, that multidisciplinary design course that I was talking about, we require most of our sophomores to take. It is co-taught. We have a faculty member like me who's responsible for the technical side, and then we have an individual from the Archer Center who is emphasizing team dynamics, leadership, responsibility, and ethics. And we've got equal responsibility in the classroom. The big thing is that you be curious, you be creative, and you be empathetic. All right, so sort of what does the program look like? First year, second year, third year. We start off roughly with some engineering sciences related courses, think math, physics, chemistry. But something that's special about RPI is very first term, freshman year, you're put into a course like Introduction to Engineering Analysis, or Introduction to Biomedical, or Introduction to Chemical. This isn't just a 1-credit survey course, this is a 3-credit modeling and analysis course that is focused on that discipline. We decided to do this about 25 years ago, and we've been doing it ever since, so when you get into the class, you can see what is ahead of you. If you take this class and say, oh my God, I hate this, please take it as a warning. If you say, gosh, this is great, congratulations, you've got a home here. But another nice thing about this introduction to whatever course is generally, oh, I took introduction to biological or biomedical engineering, I really want to get into mechanical engineering. Because there's enough similarities, the application focus was different, you could generally just move over, no cost. Similarly, then we start getting into second term, freshman year. every one of our programs has a course there, which is a great course to begin also educating you in what is in that discipline. If you decide to change disciplines, that course is a really good technical elective for all the other disciplines. So again, even in the freshman year, we're getting into engineering foundation courses. And then by the time you get to your third year, you're getting very deep in your discipline. And then finally, when we get to the senior year, you're taking all these great tools that you've learned and you're applying them to the design of very significant engineering systems. So roughly what the units look like, 28 credits approximately. Actually, most engineering is 30 credits of math and basic sciences, 22 credits of humanities, core engineering courses, 15 credits, disciplinary core courses, about 17 credits, free electives, 12 credits, etc. 128 credits total, actually civil engineering is 127, all the others are 128. It's possible to do 129 if you choose a 4-credit technical elective course. So as rigid as that may look, it's actually very, very, very flexible. It allows you, if you want, to do minors, duals, 5-year accelerated programs. I don't know if you've heard about the 5-year accelerated program, that if you're doing very well, you can go straight into a master's program and you can get a master's program in 5 years. Highly recommend it. In fact, I very much recommend it over the duals that you see up there. Some duals make sense, most don't. And a dual is that you get out in 5 years with 2 bachelor's degrees. If you're going to get a second degree, a master's is worth more than any second bachelor's degree. Okay? Again, mercenary reasons, RPI numbers. In engineering, if you look at the average plus everybody that was hired last year in engineering and what their starting salary was, and then you look at the same thing with a master's, a little over 30% higher. So with 1 extra year of education, you're starting off a lot higher. A dual doesn't get you very much. It can get you a little if you say, I'd like to call myself an aerospace engineer when I interview with this company, and I want to call myself a mechanical engineer when I interview with this company. Do not think you're impressing anyone if you say, I've got a dual in mechanical and aerospace engineering. Wrong answer. Their view is this person couldn't make their mind up. No, I'm sorry. Duals are completely used by too many students for the wrong reason. If you can do a dual in 4 years, it's great. It didn't cost you anything extra. But if you start going to 4.5 or 5 years, get a master's degree. It has much, much, much more bang for the buck. All right, so again, what the first year tends to look like, first term, second term, Calc 1, Calc 2. Of course, if you're coming in with AP credit, and many of our students do, this will change. The key is that these are actually very, very flexible. During your first year here, your principal advising will be what's called the hub, the student advising hub. We've got professional advisors. All they do is advise engineering students. The reason we think that is superior to having people like me is I'm very good at advising about courses. I'm not very good about advising about housing, financial aid, counseling, things like that, and start stepping away from the education side of it. So we've set this model up. Then in your second year, you move to your principal advisor being a faculty member, something like me. Another thing that is special about RPI is just the quality of our faculty. Again, we're a research-run institution, so we have many individuals that are fellows in the professional societies, National Academy members, Young Investigator Awards, authors of top textbooks. My recommendation to you is if you come to RPI, and I hope you do, Exploit the faculty. Most of us have open door policies, meaning if the door is open, you can always stick your head in. The worst thing that'll happen is they'll say, now isn't a good time.